Let's talk about section 2.4. Deals with continuity. And in order to introduce this concept of continuity, let me just tell you straight that a function is continuous when its graph is a single unbroken curve. Single unbroken curve, okay? This is important. If you graph your function, right, and you see that it comes all in one piece, it is connected, no holes, no gaps, all in one piece, then you got yourself what mathematicians call a continuous function, all in one piece, okay? This is what it means roughly, continuity, okay? All in one piece, connected, no holes, no gaps. Examples of continuous functions are f of x equals x squared. The square function turns out is a continuous function because if you graph it, it will show you a parabola, right? We saw it, right? And if you don't remember, you want to make sure it's a parabola, graph it, right? Y equals x squared. That's your parabola, right? Opening upward in this case, because it's 1. Great. It's all in one piece, right? So it's continuous. Another example of continuous function. G of x equals absolute value of x. When you study precalculus, when you took precalculus, they show you that the graph of this guy looks like V as in victory, right? Like this. All in one piece, connected, no holes, no gaps. It's a continuous function, right? You want to double check that that's the graph, then graph it here, y equal absolute value of x. Absolute value of x is somewhere here, right? And there you see the V as in victory, right? There we go. Continuous too. Now, trigonometric functions such as sine and cosine are also continuous. If you look at the graph of sine of x, in precalculus, they show you that this looks like a wave over a period, right? And then continues to the right, to the left, it's a wave. But what is important is that it comes in all in one piece connected. So it is a continuous function, right? Very good. Continuous here, continuous. All right. So, and again, you can even graph it in your Desmos grapher here, right? Always check, guys. Make sense of things. There you go, right? The wave over a period. Great. So these are continuous functions. But now let me give you a function. Let me give you examples of functions that are not continuous. Mathematicians call these functions discontinuous functions. Discontinuous functions. The ones that cannot be graphed all in one piece. The ones that are not connected, right? They come broken in several pieces. And as an example, I'm going to give you 3 examples, and they will show the 3 types of discontinuities that you should consider. The first one is the simplest, this f of x equals sine of x over x. Notice that when you substitute 0, when you evaluate this function at 0, then you get this sine of 0 over 0, 0 over 0, right? And then you get something undefined. The function is not defined at 0, right? Sine of 0 over 0, sine of 0 is 0 over 0, undefined. Then at 0, when you graph this function, you will see a hollow circle there, right? But the rest is okay, right? But there is it's just missing one point. And you can also check this on your grapher, y equal sine of x over x. It shows the graph. You click in here, you will see that at 0 is undefined. There we go, 0, undefined, right? So that's the holder. Now, when it's missing just one point, turns out the situation is not that bad, okay? And this type of discontinuity is the one associated to just one point missing a hole. These are called removable discontinuities. Discontinuity. It's a removable discontinuity because it is enough to place one point here and to make this whole graph a continuous graph, right? So the only thing that is missing is a point. So mathematicians call it removable discontinuity. Okay, the simplest type of discontinuity. Now there are other situations where the discontinuity is worse. For example, consider this function g of x equal absolute value of x over x. We saw this function, right? If you substitute 0 for x, you will get absolute value of 0, 0 over 0 undefined, right? So at 0, the function is not defined, right? But when you graph this function, you are going to see that it's not just that one point is missing. It's a whole segment that is missing. You will see it. Look, absolute value here.
Sorry, Professor, can you please scroll up real quick?
Scroll. Sure. Yeah, let's close this for a moment. Yeah, scroll up here.
Yeah.
More?
Yeah, more, sir.
Yeah. This was showing graphs that are continuous, right? A
Yeah.
square function, absolute value sign. But now we're showing example of functions that are not continuous. Sine of x over x, for example, has a hole here. It's called removable discontinuity. And try to remember these guys because they're going to ask you the type of discontinuities in your homework. This is called removable discontinuity when just one point is missing, hole. Now, we said that if you graph this function, let's do it together, our grapher, we will have absolute value of x, which is here, right, divided by x. Look, horizontal line here, there is a whole segment that is missing, right? Two pieces, but now it's not just missing a point, it's missing a whole segment. And undefined here, when you click here, undefined, when you click here, undefined also, right? At 0 cannot be evaluated this function. Now, when that is the case, mathematicians call this type of discontinuity a jump discontinuity, because what we have here is like a jump, right? Jump discontinuity. So jump discontinuity. And this cannot be fixed, unfortunately, right? Because if you think of padding up with points, this whole segment, yeah, you get to connect them, but the problem is that this is no longer a function because doesn't pass or will not pass, better said, the vertical line test, right? It's no longer a function. So this is unfixable. It's called a jump discontinuity, okay? All right, great. Second type of discontinuity. Now, there's another type, the third type, the last one is this. Suppose you graph the function h of x 1 over x. This is called the reciprocal function, right? In the first lecture, I talked about it. Its graph is this. If you don't remember, just type on your grapher 1 over x and the graph will come out. It shows here a huge discontinuity because this is not just a segment. Remember, guys, I told you this graph never touches the y-axis. This part never touches the x-axis. It's a segment there, but with infinite length, right? So it's worse than this, right? This is bounded, this segment, this is unbounded. So this type of discontinuity mathematicians call an infinite discontinuity, right? Because what is missing is this whole line, right? There's no way to fix this. So this infinite discontinuity. Infinite discontinuity. All right, so this is the third type of discontinuity. And I hope at this point you will be able to identify it, right? Plus infinity here, minus infinity here. That's what they call it, infinite discontinuity. And it always shows a vertical asymptote here, vertical asymptote. All right, so now guys, first, I want you to be able to identify these three types of discontinuities clearly, because it's gonna help you a lot. So we're gonna go over some exercises first, quickly, right? And then we'll go over this computational stuff. Yeah, so here, quickly, identify the discontinuity and the type of discontinuity, if possible, in the chat. Okay. So number one, look at this graph. They say find all points where the function is discontinuous. At which point this function is discontinuous. And as a hint, I will tell you, look at this hollow circle, right? And look down here, see where that happens, right? At which input value? 4, excellent, right? At 4. And what would be the type of discontinuity, in your opinion? Is it a removable discontinuity, a jump, or an infinite discontinuity? What would be a hole, right? It's removable discontinuity, x equal 4. Excellent, excellent, very good. What about number 2? What type of discontinuity we're dealing with at what input value? Here, attention here to this piece. This piece missing.
A jump.
Here. A jump. Excellent, excellent, right? Excellent. A jump discontinuity. Jump discontinuity.
1.
It was a whole, right? At 1, right? Happens at 1. Yeah, excellent, excellent. This guy, right? And this, the last one, the number 3.
Infinity.
Infinity, right? Yeah, very good, guys. I see in the chat also, it seems I'm writing the vertical axis here, and this happens at 3, right? So this, just to make sure that everybody's okay, infinite discontinuity, right? Infinite discontinuity here. Excellent, excellent, guys. You will be asked to identify this type of discontinuity in your homework, right? I'm glad that you're good. All right, now computational stuff, right? So let's go back to the worksheet, not to the worksheet, to the lecture. And let's talk about precisely what happens when the discontinuity happens at a point. Mathematicians' formula define the continuity at a point by saying that a function f of x is continuous at a point k if and only if the following conditions are true. Evaluation of the function is defined, meaning you don't have holes there, right? You have a solid circle. The limit exists when you approach to k, if you are talking about this continuity at k, right? And not only that, the limits should match with the evaluation. And this is where continuity is going to help us with evaluation of limits, right? If your function is all in one piece continuous, you are allowed to plug the value into in order to find its limit, right? This is what it's saying. So example here, suppose they give you this piecewise function, given the function f of x equals sine of x over x if x is not 0, and f of x equal 2 if x is 0. Question, if x continues at x equals 0, let's check the 3 conditions, right? First says f of 0 must exist. It must be some number. F at 0, according to this definition, is 2. So this checks, right? Good. The first part, good. It's defined. There is no hole there. There is some solid circle there. But now, the limit, does it exist? Well, notice, the graph of this guy, we know, is this, right? We have shown several times, it's like this. And from the left, if you approach from the left, you're going to 1. If you approach from the right, you're also going to 1. So the limit exists, that not only that is 1, right? So this is good. Right? The limit of this function, as x approaches 0, is 1. It exists, it's good. But now, is the limit equal to the evaluation? Well, the limit is 1, but the evaluation is not 1, it's 2. It's 2, right? They don't match. Look, no, false. So just because of this third condition, you have to say as a conclusion, f of x is not continuous. It's not continuous at x equals 0, right? So it's not continuous at x equals 0, right? So this is how this works. Now let's go back then to the exercises. Yeah, let's see if this one we can do. Continuity on an interval, so we need more information. All right, now yeah, we have this continuous at a point. Now in order to do this, yeah, so continuity over an interval we need, right? But now in order for you to do your homework, let me give you two more examples, okay? Example 2 says, giving a function f of x equal x squared plus x minus 7 over x squared minus 1. For what real numbers is the function not continuous? For which of this is the discontinuity removable? Removable. This is something that you have to do in your home. So let me explain this to you. If you are giving a function like this, solution first, let's factor the numerator and denominator to see if we can simplify this, right? So let's do that. X here. Two numbers whose multiplication is minus 7, whose sum is 6, are after some trial and error, 7 and 1, minus 1 plus 7 here. Denominator factors as x minus 1 multiplied by x plus 1, right? Difference of the squares. Right there, you notice that there is something that we can cancel, which is this factor, right? X minus 1, top and bottom. Let's cancel them. And what is left? X plus 7 over x plus 1, right? Now, for which values is this function discontinuous? Well, for that, I want you to look at the denominator, right? On the denominator, and you are going to take the opposite numbers of this. Minus 1 here, plus 1, opposite. And for this, opposite of plus 1, minus 1, right? Is discontinuous at these two input values, 1 and negative 1. It's not continuous, right? But where the discontinuity is removable? Well, notice that we have removed this factor, right? And indeed, we ended up with this. We were able to fix this part, right? So the discontinuity will be removable for x equal 1, right? But not for this. Look, for this discontinuity stays, right? Stays. You follow, guys? When they ask you for removable discontinuity, look at the factor that you were able to remove. Yeah, for the other one, yeah, very good, very good. Yeah, great, good. Yeah, so this is how you figure this out, right? So another example here. Again, they give you a function. They say, for what real numbers is this function not continuous? So what you have to do, and then for which of these is the discontinuity removable? Again, factor, right? Factor this, whatever they give you. In this case, this will be factored as x. Two numbers of multiplication is 35, sum is 2, 7 and 5. This minus, this plus. Denominator factors as x here. Two numbers of multiplication is 5, whose sum is 6, are minus 5, minus 1. Now you notice that these two guys are the same, right? So you cancel them. But what stays? Well, x plus 7 over x minus 1, right? So the discontinuities are, again, take the opposite of this. Opposite is minus 1 here, so plus 1. And opposite of this. Opposite 5, right? These are the discontinuities. The function is not continuous at this, not continuous at this. But it has a removable discontinuity at x equal 5, because remember, we were able to remove this factor, right? So at x equal 5, the discontinuity is removable, right? Yeah. Very good, guys. So that's hope you will be able to follow this example to deal with your homework, okay? All right, now let's talk about continuity over an interval. Mathematicians say that a function f of x is continuous over an interval if it is continuous at every point of the interval. For example, this function, g of x equal 3 if x is greater or equal than 2, an identity function for x between 0 and 2, can be graphed, and after you graph, they're asking you, is g of x continuous over this interval if g of x continuous over this other interval? So let's graph it first. 3, constant function for x greater or equal than 2. Greater or equal than 2. So for this constant function, 3. So 3. So farther here, up. 3, right? So 3, constant function, solid circle, notice very long or equal. So this is this part, right? This is this part. Now here, identity function for values, input value from 0 to 2. So here identity function, right? So we'll go like this, but a hollow circle here, because at x equal 2, it's a constant function, right? Very good. Yeah, but let's do it nicer because it has to be a diagonal line, right? That's better. Yeah. Now the question is g of x continuous on 0, 1? From 0 to 1, yes, because you are here, right? From 0 to 1, you're here. From 0 to 1, you're here. For this part is a continuous function, right? It's all in one piece. So this one, yes, from 0 to 1. I want you to pay attention to this interval. Here, yes. But now, is the function continuous over the interval from 1 to 5? From 1 to 5, the interval goes from here to here, right? Look up. Look, there is a jump there, right? So answer no. Jump here. No. Very good, right? So that's how it goes, right? So note, if a function f of x is continuous at every point in the interval from negative infinity to infinity, then we will simply say that f of x is continuous. So if you see that your function is continuous over the whole real line, then you will say simply that the function is continuous, right? Understood that the interval for the continuity is this, right? Now, another thing that I want to show you guys, sometimes students, when I do this graphing, right, say, Professor, is it possible for us to graph this in our grapher? The piecewise functions? Answer yes. I will show you now, okay? Let's say you want to graph this in your graphing calculator. This is going to help you a lot. Well, then you have to follow this. First, you're going to write 3, or y equal 3, or just 3. But from where to where? From 2 up, right? For x greater than 2. The way you tell that to Desmos grapher is this. Between braces, you write x bigger or equal than 2. Okay? Then you close braces. You see, graphs just this piece, right? This is this. Now, the other part, you want the identity function y equal x or just x, but from where to where? From 0 to 2. So within braces, again, you do from 0 less than or equal, right? Less than or equal. X here less than 2. Close braces. The braces are important. Then this part. You see, guys, this is what we have here. Of course, this thing for these details, you have to go here, look here, and define the hollow circle. Here is well defined. 2 goes with 3, right? But it helps you, right? This is this. Okay, great. All right, moving on, guys. Moving on. Now, let's go to the worksheets. But before we go there, examples of continuous functions, the ones that come all in one piece, polynomial functions, they are always continuous. The sine function is always continuous. We saw the waves. Cosine is also continuous. You saw the waves. An absolute value function, right? Absolute value function. Now, what's the big deal of a function being continuous? Well, here is a big deal, guys. Composite function theorem. If your function is continuous at some value a, some real number a, and the limit of some other function as x approaches a is equal to this L, then you're allowed to put this limit inside the function f that is outside, okay? You follow, guys? Basically, to put it simple for you, right? If you find out that your function is continuous, in order to find the limit, you just have to plug this value into the other function, right? So how does it work, Professor? Well, suppose they ask you to compute the limit of this cosine function, right? We know that the cosine function is continuous, right? It's continuous, right? Professor, how do you know it's continuous? Well, if you have doubts, graph it. When you go cosine of x, they show you in precalculus that is this, right? Continuous, all in one piece, doesn't show holes, doesn't show jumps, it's continuous. So since it's continuous, basically, you are allowed to put this limit in, which translates itself as just plugging the value into, right? Into this, you will see. So if they ask you for this limit, this is just this, okay? It's like plugging the value into, right? The pi over 2 there in the end, because now it's a linear function I plug the value into, and look how easily you get your limit. You get this, so your limit, right? Pi over 2 minus pi over 2 is 0. Cosine over 0. But what is cosine of 0? Is 1. It's very counterintuitive, but if you don't remember, you just compute it. Cosine of 0. Make sure you're working in radians. 1, right? Degrees or radians, 1. Great. So this is how you work. You take limits when the function is continuous, right? Cosine is continuous. That's why we were able to plug this guy into. I want you to kind of stay with this idea, right? We ended up with this. Similarly here, another one. Look, sine function I know is continuous. So that allows me to just put this in, right? Formally, what you are doing there is this, right? Sine of, you put the limit inside, right? Limit of x minus pi. X approaches pi, right? X minus pi. But in practical means you end up just plugging this into again, right? So sine of pi minus pi, but pi minus pi is 0. So sine of 0 degrees or 0 radians, better said, right? Because this doesn't have the, it's in radians because in calculus, unless specify, everything is worked out in radians for the angles, right? So 0, sine of 0 is just 0. There we go. Okay, guys, so now let's go over some quick exercises. And then let's talk about the intermediate value theorem, right? So let's go back to our worksheet and follow your common sense for this continuity business. I hope you will be able to do this. For example, right? What would be the answer for this question? Is the function whose graph is this continuous over this interval? Anyone could answer it? Over the interval minus 4 and 2. Minus 4 and 2 is here. Minus 4, minus 2, sorry, and 4. Over this interval. Is it continuous, this piece?
Yes.
Is it? Be careful there.
No.
No. Someone said no. Yeah, Adrian,
No.
yeah, no. Oscar, no. Yeah, no, right? Yeah, the problem is that over this, look, there is a jump there. You see it? Yeah. Yeah, it's tricky though, right? Yeah, but over this interval, look, notice there is a jump. Jump, right? Jump discontinuity. So because of that, if they would have said from -2 to 0, yes, continuous, right? All in one piece. From -2 to 1, all in one piece. But when you say from -2 to 4, there is a jump there because of that. No. Very good, guys. Now, question number 5. Question number 5. Another question here. Now they are asking you to figure out over which intervals the function is continuous. Can you figure this out? Try this. Follow your intuition. Wherever you see that the function is broken, you gotta say that it's not, right? Yeah. But probably we should do it together then. If you start going over the function, yeah, I think students already figured it out. CG, yeah, very good, CG. Yeah, very good, excellent. Yeah, yeah, let's try it right together. This piece is continuous over what interval? Look, this from here to here. This piece continues over what interval? From negative infinity, let's write the interval here, negative infinity, up to what number? Up to 0, right? Up to 0, yeah, there. Then the other interval, for continuity would be this piece, right? This piece also another connected component from 0 to 1, right? Notice now that the 0 is close with a solid circle. That's why I'm using brackets up to 2, right? Up to 2 brackets. Okay? And finally, there's a jump here, but then another connected component here, right? This blue piece. This happens from 2, not touching 2, hollow circle, right? Up to this continues, right? Forever to infinity, up to infinity. So we are talking about this guy, right? I think it's this. It's negative infinity to 0, 0 to 2 with brackets, 2 to infinity without brackets, right? Very good, very good. Yeah, this is the definition, so I think you can do it at home. I want to show you this one. This is a very important part. What to do when they ask you to figure out a value on a piecewise function such that this whole function is continuous. Find a value of a so that the function f of x is continuous. I will show you a nice strategy so you can apply that and figure out these values. This is a parabola, right? This is a linear function. How can we make sure that the parabola will connect with this, For that, you're gonna do this. The limit of f of x as x approaches this guy 4, because it's here where the connection happens, right? From the left should be equal to the limit of f of x as x approaches 4 from the right, 4 again from here. This will guarantee that these two guys will click, right? Be connected. So now this limit, for this limit, I use this function, right? This function here on the left, because this guy is dealing with values, input values on the left of 4. So I use this guy, right? On the left, maybe I can write it here. So I do 4 squared minus 3 here should be equal to, for the limit as I approach 4 from the right, I use this 5 times a times x, but x is 4, right? And this equation will give me a way to find the value of a, right? 5 times 4, 28. 4 squared 16 minus 3 is 13. 28. Dividing both sides by 20, you get your answer, right? You follow, guys? You make the left limit equal to the right limit, okay? That's it. Yeah, this is a very common exercise, so you should know about this. I did this for you. Take this as a reference and try to do the next, this guy. Okay, I will leave this as a reference, okay? So you can follow. Same idea, but figure this out. Okay, do this. Yeah, I'll be right back, okay? I'll be right back. Okay, great. So any answers for number 8? Try to take the limit from the left, the limit from the right, and then you should be fine there. Yeah. All right, let's do this together then, right? Together. Again, the idea is to look at this number 3. Is where the two parts of the graph, the quadratic part, the parabola, and the cubic part should meet, right? So you have to take the limit of the function as x approaches 3. Aha, I see. So move it on the chat room. CG, yeah. CG, yeah. You got it. Very good, very good. Yeah, you made my day. Excellent. Great, great. Grace, Adriana, CG. Great, guys. Very good, very good. Yeah, so let's take the limit from the left and make it equal to the limit of the function from the right to guarantee that they will connect there, right? They will connect. That's the whole idea. So this guy, for this guy, I have to use this formula, right? 3 squared plus 3 plus a. For this guy, I have to use this other formula, 3 cubed, right? Because you deal with numbers on the right there, 3 cubed here. Careful. Do the math. 3 squared is 9 plus 3, 12 plus a equal 27. Subtract 12 in both sides, and then you will get that a is just equal to 1 here, 5 here, 15, this guy. Excellent, excellent, very good, guys, very good, right? So then you can do this at home, right? Same idea, same technique. Let's talk about the last part then, the intermediate value theorem, okay? Yeah, very good, very good. So what is the intermediate value theorem? It deals with the following. It tells you that if a function is continuous, then since it's all in one piece, if you evaluate your function, let's say, and it is positive at some input value, and you evaluate your function again and it is negative, then if your function went from a negative value to a positive value continuously, all in one piece, right? It means that it has to go through the x-axis, right? It has to go through 0. It has to go through 0. That's the main idea of this theorem, right? To put it simple, guys, if you live in a building, if you want to go from the basement to the 4th floor, you have to go through the main floor, right? Somehow. This is the whole idea of the continuity, right? Yeah, so mathematically speaking is this. Let f of x be a continuous function on an interval a comma b. If z is any real number between f of a and f of b, right? Then there is a number c in a comma b such that the evaluation of c has to be equal to z. What does it mean? Well, suppose your function is continuous over this interval from a to b, right? This says this, all in one piece. What this is saying is that if somehow you have a value between these two, f of b and f of a, let's say this value is z, as in zebra, z here. What the theorem guarantees is that if you go back to the function, since it's continuous all in one piece, you will hit the function such that you will be able to find at least one input value c between a and b, as you can check here, right? Such that f of z is z, right? Now, the theorem tells you that at least you will find one input value, but perhaps given the shape of the function, you may be able to find not just one value, but two. For example, suppose you have this situation here. Okay. And well, in this case, let's say there is a z here, right? The function is continuous. If you go back to the function, you will hit it more than once, 1, 2, 3 times. So there will be 3 c values. Let's say c1, c2, c3, right? But what is important is that at least one value can be found, right? So that's the important thing. And because of that, mathematicians use this theorem as an application to find solutions for polynomial equations or even equations in general. As long as there is continuity, they use this theorem in the following way. Application here: if f of x is a continuous function on the interval a comma b, it's all in one piece connected over a comma b, and f of a and f of b have different signs. One evaluation is positive, the other evaluation is negative, or vice versa, right? Then there is at least c between a and b such that the evaluation at c has to be 0, because remember, guys, it went continuously from a negative value to a positive value, right? Continuously. Let's say from here to here, right? So this is in general, let's say this is a and b, right? The evaluation at a is negative, evaluation at b is positive. Since the function is continuous, then it has to go through x-axis, right? It has to hit x-axis. This is the c. This is one scenario. The other scenario is this. If the evaluation at a is positive, let's say a here, f of a, and the evaluation at b is negative, say down here, well, since your function is continuous, no matter what, it has to hit the x-axis at some value c, right? C. So to put it simple, guys, you have to simply verify two evaluations. One evaluation must be positive, the other evaluation must be negative. And if you do that, then using the theorem, you can say that there is going to be a solution, right? At least one solution over some interval. Great. Okay, so let me show you this example. So it's not difficult. It says here, provide an appropriate response. Use the intermediate value theorem to prove that this polynomial function, right? Negative 2x to the 4 plus 6x cubed plus 5x minus 2 equals 0 has a solution between the numbers 3 and 4, okay? So what I do is first I say, okay, let this guy be my function, right? Let f of x be negative 2x to the 4 plus 6x cubed plus 5x minus 2 be my function, right? And I do a couple of evaluations. First evaluation, I do it at this value 3. Why at this value? Because this is like the a, right? F of a. And the next evaluation, I will do it at 4, okay? So the second evaluation will be at 4, will be here. I will write f of 4. And I just have to make sure that these two evaluations have opposite signs. The evaluation at this guy is this, right? Q plus 5 times 3 minus 2. And if you put this in your calculator, you're going to get the number 13, which is positive. Okay. Right, good. Now, if you evaluate at 4, you have to substitute x with 4, right? You will get this, right? That's 5 times 4 minus 2. Turns out when you do this computation, you're going to get negative 110. Good news, right, for us, because remember, guys, if there is a continuous change of signs on the output values, it means that you have to go through 0. But going through 0 means that there is going to be a solution, right? There is going to be a solution. So then you can say, I can even draw something for you to understand it, right? At 3, we got some positive value, 13, right? 13 here. This was the first point, the first evaluation. And at 4, we got some negative value down here. It was negative 110, right? Negative 110. So this means that since the function is continuous only in one piece, no matter what, you have to hit this at least once, right? So here is the C, right? They ask you to find, right? And they're just asking you to show that there is a solution. They are not asking you to find a solution, right? Because that would be difficult. They use the intermediate value theorem to prove that this equation has a solution, right? So you can write here, based on the intermediate value theorem, then there is a solution in this interval, right? In 3,4. So this guy is between these two values, right? So there is a solution. This is the idea. Can you try the number 2? It's similar, right? Try to do this number 2. Use the intermediate value theorem to prove that this polynomial function has a 0 between -2 and -1. There is a solution for this polynomial equation, right? Can you try? Let me give you a hint. Let f of x be equal to this guy, 7x cubed plus 9x squared minus 6x minus 5. And then do a couple of evaluations, right? First evaluation should be done here. First value of the interval right there. And the second evaluation should be done at this other guy. And try to remember this for your homework, guys. There's some couple of 2 or 3 questions related to the intermediate value theorem, but this is what you will need, right? So try to do the 2 evaluations and show me what you get. And let's verify, right, that there is a change of signs, which will guarantee the existence of a solution, right? Mm-hmm. Use your calculator, right? It's just, yeah. Yeah, great. Yeah, the first evaluation at -2 should be done this way, right? And probably this time I will show you how to get it in your calculator, right? In case this is gonna be the first evaluation, right? And the second evaluation should be this, right? -1 cubed plus 9 times -1, 6 times -1, -5. I see students figure this out. Very good, Oscar. Yeah, you notice, right? There's a change of sign. It could be from positive to negative, but also could be perhaps from negative to positive. What we really need is just a change of sign to guarantee that you gotta go to 0. Yeah, very good, very good. Very good, very good. Yeah, this time, guys, I'm gonna do it using the calculator, okay, for you to see how you compute this using your scientific calculator. Well, you start with 7, then you use parentheses. Very important to use parentheses because we're evaluating this expression at a negative input value. So without the parentheses, it's not gonna be correct, the computation. You have to use parentheses. Plus what? 9 times. Notice to avoid using this multiplication sign, I'm just writing next to 9 the input value -2 within parentheses, right? Within parentheses. Minus 6 times -2 within parentheses, -5. Yeah, so I get there, let's see.
Did we have to drop the x squared, the 9x squared?
No. This needed there. Yeah, this I didn't write it, but it's needed. Yeah, it's -13, right? Yeah, this one too. Yeah, thank you there. I didn't write this too, right? Yeah. Whenever these kind of things happen, guys, when you are working on your homework, or even when you are doing your exams, right? Something doesn't make sense. Just go back to what you did, and you will find it. I didn't write this two from here, right? So now it's good. Let's bring back our calculator. Negative 13, right? That's what you got, right, Oscar? Negative 13. First computation. Great. Now I need to do another computation that is similar. I advise you to do this, guys. I give you this advice. Just copy and paste this, right? Copy and paste. And just change the input value. The input value is now -1. So instead of -2, now -1. Very good. Very good. -1. And look, -13, negative the first computation, and the second computation positive, which is good news for us because it tells us that we can use the intermediate value theorem, right? That is why it's called the intermediate value theorem, because it deals with the number in between, right? In between. So we're gonna write the output values here, -13. In this case, is negative, right? Which is the other scenario, right? There's two possible scenarios, negative first, and now the second was positive, right? So if you want to visualize this in an XY coordinate, well, this is what is happening now, right? Now they are talking about this guy -2 first, which is here. The evaluation gave us a negative number, so somewhere on the bottom here, right? It says negative here. And somehow when you use evaluation at -1, when you plug into your function -1, somehow the output value was positive. So they're talking about something above here, right? Above the x-axis. But what is important is that since this function is a polynomial function, it's a continuous function, right? It's all in one piece. So it's going to go like this. So it has to hit the x-axis, right? No matter what. And this is the guarantee that there is a solution. That's the solution, right? They're not asking you to find a solution, right? They're just asking you to show, to prove that there is a solution, right? Very good, very good. Great, great, great. Just to clarify what's positive and negative and negative, that would mean that solution. Yeah. Yes. There is this, Oscar is bringing this up. In case you get here positive, and let's say you get here positive again, then there is no guarantee, right? There's no guarantee because the output values could stay on the top, right? They may not cross, right? They may, but they may not. There is no guarantee. Or if you get negative and negative, then your answer should be no, right? There is no guarantee that there's going to be a solution. You follow, guys, right? Only when there is a change of signs is there when you can apply the intermediate value theorem, right? Otherwise, you have to reserve your judgment. You say, no, nothing to say, right? Yeah, before going, let me give you a hint for this. This is a little bit tricky. Professor, what if the equation looks like this? Here, there's no 0, here is 2, right? Before you gave us something with 0. What to do? Well, first, the hint is here, right? First, subtract 2 in both sides, right? So, subtract 2 in both sides. Why, Professor, we are subtracting 2 in both sides? Well, that way this guy will come here, right? So then we're kind of back to normal, 0 here, right? As before. And then you let your function be equal to this guy, right? So in case 0 is not on the right, you subtract whatever you have here, and then 0 will appear, then this will be your function. And then you do the couple of evaluations. In this case, the first evaluation will be, they want solutions between 1 and 3, right? So at 1, and then evaluation at 3, this will be 1 times 1 minus 2 squared minus 2 is minus 1, negative, right? Which is good. Well, we see what's the other. The other will be 3 times 3 minus 2 squared minus 2. This is 1, 3 minus 2, 1, positive. Good, right? So then there is a C, right? So good. And this is similar, but again, here, hint, subtract x in both sides, right? And once you subtract x in both sides, let f of x be equal to 4 times sine of x minus x be your function. This is a continuous function because sine is all in one piece, the identity function all in one piece. So then you should be okay here, right? And then you just have to do the couple of evaluations, one evaluation at pi over 2, notice, and the other evaluation at pi. The evaluation at pi over 2, believe it or not, guys, gives you this 4 times sine of pi over 2 minus pi over 2. This number is a decimal number, 2.42, once you evaluate. But what is important for us here is that it is positive. When you do the evaluation at pi, you are going to get 4 times sine of pi minus pi, which is 3.14 approximately, right? And you're going to get negative 3.14, negative, right? Then there is a solution, right? Based on the intermediate value theorem. Solution in this interval from pi over 2 to pi, right? Based on intermediate value theorem.